Hi dears, today we can see CSIR NET max problems from real analysis. First question, let R denote the radius of convergence of the power series summation k equal to 1 to infinity k x power k, then 4 of the option is given. So first of all we can find the radius of convergence. So for that the given one we are taking summation k equal to 1 to infinity ak x power k, which is equal to, this is the given one, k equal to 1 to infinity k x power k. So here ak is equal to k. So the radius of convergence limit n tends to infinity an divided by an plus 1, which is equal to limit n tends to infinity an equal to n divided by n plus 1. Take n outside, we are getting 1. So r is equal to 1. So from this option for 4 is false because r is equal to 1. Let's see the other options by checking the series convergence. So for that we know that the radius of convergence in the power series converges if modulus is x less than r and diverges if modulus x greater than r. So this represents x modulus x less than r means x belongs to minus r comma r. That means x belongs to the value of r is 1. So here minus 1 comma 1. So this is converges for this value. This is okay. But what about for exact 1 and minus 1? That is close to minus 1 and this one. So minus 1 and 1 included means what had happened. Whether it is converges or diverges. That we are going to check it. So for that, let x is equal to 1 and the next case x is equal to minus 1. So summation k equal to 1 to n ak x power k. In the place of x you can substitute 1 and ak already we have as k. So that is. So for finding just put limit n tends to infinity an. The value an is equal to here k. ak is k, an is n. So applying limit, we are getting infinity, which is not equal to 0. This said that the series does not converge at r is equal to 1 because x and r we are taking as 1. Okay, so at r equal to 1, the series does not converge. Let's check for x equal to minus 1. So here in this place of x, we are substituting minus on the whole power k. Since this is an alternate series, that is minus 1 plus 1, like that alternate series, we have to use the Leibniz test. So for that, limit n tends to infinity modulus an equal to limit n tends to infinity. Here in the place of an, here we have n, right? ak means k, an is n, which is equal to infinity, not equal to 0. So this series also does not converge at r equal to minus 1. So exactly at minus 1 and 1, the series does not converge. So we can say that r greater than 0 because r equal to 1 greater than 0 and the series does not converge outside. If it is inside, according to this condition itself, it is converges. But it is outside, it is does not converge. That is at 1 and minus 1 itself, it is does not converge. So you can see that option C is the, that is 3 is the correct one. Let's see the next question. F from R to R is such that f of 0 equal to 0 and modulus df by dx less than or equal to 5 for all x, we can conclude that f1 is a. So the given is these two. So f of 0 equal to 0, accordingly you have to take a function. I am taking the linear function, that is a plus bx. So given you are substituting and the place of x substitute 0, from that you will get a is equal to 0. Again you substitute here fx is equal to 0 plus bx, that is fx is equal to bx. Now if I am differentiating, I have to get less than or equal to 5. So if I am differentiating, I will get 5, right? So that I am choosing b is equal to 5. So 5x. Now we have to find f of 1. So f of 1 is equal to 5. So here 5 is not included. Here we have 5. Here 5 is not included. Here 5 is included. And here not included and not included. So from this we can verify that option B is the correct one. Next question. Let En be the sequence of subsets of R. Define these two, limit supremum and limit infimum. Which of the following options are true? So here R is given, which is not defined as whether it is convergent or divergent. So the first option is true only for the convergent series. Okay, limit supremum equal to limit infimum, this is possible only for the convergent. But at the question it is not given whether it is convergent or divergent. So accordingly we can say that the first one is the wrong option. Let's check the other options. the given one limit supremum is equal to intersection union En. So if X belongs to limit supremum En means X belongs to limit supremum is equal to this value. So we know that if it is union means in words we will write for some, right? And for intersection means we will write for each. Okay, so that concept we are using here. So X belongs to intersection union En. That means X belongs to union En. For intersection we can write for each K. That means infinitely K. K carries 1, 2, 3, etc. up to infinity. So X belongs to union En, you can write as X belongs to E1. That is for some. X belongs to E1 or X belongs to E2 or X belongs to etc. for each K. So here we have for some and for each. Okay. Infinitely. This means infinitely. So from this you can say that limit supremum. Here it is given for some, but we get infinitely. So accordingly we can say that option B is the wrong option. Okay. We have to get here infinitely. Let's see the third option, that is limit infimum. So limit infimum is equal to, this is the given one. So X belongs to limit infimum En, that is X belongs to this value. So for X belongs to union K equal to 1 to infinity, for this one I am taking as BK. Otherwise you can use this technique also, okay? BK, where BK is equal to what? This value. So union means for some, right? So X belongs to B1, X belongs to B2, etc. for some K. Now, in the place of B, here we have intersection. So X belongs to intersection En, but here for some values. Okay, for some B only this is possible. Now, for intersection, what I can write here? For each. Okay, infinitely. And here for some means for finite cases. Okay, so you can write in words as for all, but infinitely. So you can see option C is the right option. Okay, for all, that is for each, then but finitely, that is for some, that is also included. So option C is the right option and option D is wrong. Let's check the next question. Which of the following are countable? So for this one, the option set of all polynomials with a rational coefficient. Second, set of all polynomials with the real coefficients. Again, there also next to C and D also real and rational eigenvalues. Then real whose rational entries. So for all this, we might be know this one. The set of all rational number is countable. That is cardinality of Q is equal to alif naught, which is countable. Similarly, set of all real numbers is uncountable. That is cardinality of R is equal to C, that is uncountable. Okay. So here set of all polynomials is with the rational coefficient. So rational, here rational is countable. So option A is the right one. Let's check the second one. Set of all polynomials with a real coefficient having rational roots. Rational roots, but what about the polynomial coefficient whose are real? Real is uncountable. So option B is wrong. Let's see the third one. Set of all 2 by 2 real matrix with a rational eigenvalues. Eigenvalues are rational, but the matrix itself real entries. So real is uncountable. So option C is wrong. Let's see the D, set of all real matrix whose row echelon form has rational entries. Entries are rational, but the matrix are real. So option B is uncountable. So the only one option is right, that is A, which is countable. Thank you.